using Hello all. Can you hear my voice?
Yes, we are hearing you.
Okay. Hello everyone again. So
okay. So I think my name is Sotner. I am from Brno University of Technology. I will be sharing this session. I don't think there is some moderator or someone which will giving us some information. So there are 4 papers in this session. So we will start with the first one. I think we have 15 minutes for presentation and then some time for discussion. So we have, I think, 1.5 hours to proceed this paper. So I may ask the first presenter to share your results, the results with us, and then we can discuss. So the first presenter is Mehmet Arslan from Bursa Technical University, and the paper has name Design and Validation of Acoustic Temperature Compensated-Based Fpg sensor package for air vehicle applications. So the word is yours, colleagues.
okay, sir. So I'm beginning with your excuse.
Okay, we can
see my screen.
Yeah, we can see it.
Okay. So before beginning, I would like to thank you all for your attendance and leaving your time for the presentation. Let me just briefly introduce myself. My name is Mehmet Mucahit Arslan. I was born in Turkey and traveled to Malaysia for degree purposes. I have taken my degree from the Malaysia Asia Pacific University in the major of telecommunication engineering. And I'm doing my master's in Bursa Technical University along with assistance of Gokay Bayrak. So today's topic will be actually based on optical fiber sensing. More precisely, I would say FPG sensor package. And just let me repeat the title. Design and validation of an effective temperature compensated-based FPG sensor package for air vehicle applications. As for now, I am working in Turkish Aerospace company. We are facing with some troubles in terms of temperature compensation. So I'm doing my thesis. Sorry, there's something written in the chat.
So please, colleagues, move with the presentation into full screen, then proceed page one by one, because we are seeing the first slide of the presentation only.
Okay. So just give me a second, sir, please. Excuse me. Excuse me, sir. So you can still see my screen, right?
Yeah, just switch to full screen, please. F5, I think, is the...
Yeah, okay. Now is it clear?
No, we are seeing it in editing mode, not in full screen.
Actually, I'm doing F5 and going to the full screen, but I think you are still seeing the same thing. Okay, let me just stop the share and reshare it, maybe.
Yeah, just try. You have to, I think, share the full screen of your computer, not only application.
Okay.
No, not only window.
Okay. Now better?
Still not. Now,
Now
super.
fine, right? Okay.
Super. Thank you.
Okay. Sorry for taking your time. So let me just briefly introduce the content of today's topic. At first step, I will be talking about the basics of the fiber break gratings, which will be followed then by FPG manufacturing methods and FPG sensor working principles. Right after that, I will be talking about the temperature compensation at FPG sensors and importance of the temperature compensation in general air vehicles and UAVs. And finally, I will be talking about the tests we have handled and the results obtained just according to those tests. So let's begin with the basics. Actually, the fiber break grating is a unique type of break reflectors. Those are observed just by chance by the Bragg brothers in early 80s. So here, I should say that Bragg reflectors are some sort of structures that are observed by periodical refractive index modulation and growing the dichroic mirrors within a limited segment of optical fibers core. Okay, here, the most important point is that the gratings are only observed by the fiber's core, and we have nothing else to do with the other layers of the optical fiber. And so let me just produce further. This mentioned period is generally in greatly constant status. Of course, we have some other examples, just like tilted Fpgs. In these Fpgs, in this kind of Fpg sensors, we are called tilted Fpgs. There's some sort of variation in the periods of the gratings. So as a result of growing dichroic mirrors, or we can call them fringes, Fpgs act as an wavelength filter. Of course, this filtering is happening based on full width at half maximum and side lobe suppression ratio properties. So as a result of what I have said so far, okay, as a result of what I have said so far, you can see the picture just in the bottom of the page. There's only one specific wavelength. There's only one specific wavelength reflected, and all other wavelengths are transmitted through without getting affected of any change. Okay, so let me just talk about FPG manufacturing methods. As I mentioned previously, fiber break gratings are some sort of sensors. They need to be handled, manufactured, and used very precisely and carefully. So in this manner, we have the three essential types of manufacturing techniques. And some of them is traditional and some of them is relatively novel. So let me just begin with the traditional one, that we call it point-to-point. In this point, I must say that there is no, like many companies or individuals using point-to-point technique anymore. It was a traditional and past technique, because in this technique, there are 4 or 5 types of mirrors and reflectors. And you have to position these mirrors and reflectors perfectly. And in this point, another important case is that we are using 7-8 nanometer femtosecond laser, and you have to direct the light coming out from the laser perfectly. And also previously mentioned that the grating period should be so precise. So in order to achieve this precisity in the core of optical fiber, one's actually basically need to position the points extremely precise. So we don't have even in the current technology. Just now we have, yes, but previously we didn't have such sort of motors, servo motors, and so on, just to position the optical fiber in terms of micrometers. So thereby, I must say that this technique is, of course, it's relatively lower cost, but the process takes a lot of time, and it has a relatively lower accuracy as compared to others. And besides that, FPG sensors are famous with being an array structures. So if I use point-to-point technique, it will be like it's extremely hard work for me to come up with an array structure. So the second method that's also very rarely using in today's world, the draw tower technique. This technique actually allows us to manufacture the FPGs with highest durability, and it allows for multi-point FPG array manufacturing, and there is no limitation in this technique in terms of FPG array manufacturing, but as compared to other techniques, it has the highest manufacturing cost, highest maintenance cost, and it's extremely hard to control. That's why only few companies nowadays manufacturing FPG sensors by considering this technique, and their products are much more expensive than the conventional ones that we can just find in industry. The last technique is face mask. I must say that this is the one that we have preferred in this thesis, in this study. With this, actually, face mask technique is, we might say that it's more compact and more controllable form of the draw tower technique. Okay, in this technique, just similarly to the draw tower one, we have a UV light source. That's maybe you can see in the picture that there's a green lens, focus lens, and the UV light source of 193 nanometer is coming through the focusing line and phasing entire light with the focusing length and letting it through, fall into the face mask. Okay, this face mask is, it's something that we have to just stop and mention about it. Face mask, as shown in the picture, is basically manufactured with the E-beam lithography technique, because the grating period in the core of the optical fiber is in terms of nanometers, and the face mask, the fringes in the face mask should be half of these values. So with physical manufacturing techniques, it's really hard to get this precisity, but only with the electron beam lithography techniques. So in this technique, we are following the UV light into the face mask and then making some sort of pattern and following this pattern into the core of the optical fiber, and eventually we are getting a grating structure. Okay, this structure allows us to have a much more control as compared to other ones, while reducing our manufacturing cost and maintenance cost. Also, just like the draw tower one, with this technique we can achieve multi-point FPG array manufacturing, which is one of the most valuable advantages of the fiber break grating sensors as compared to conventional strain sensing sensors. So let me just continue with the working principle. Okay. Fiber break gratings can be used in variety applications, such as strain sensing, temperature, pressure, vibration, and acceleration sensing. Okay, here we have to mention that basically, I'm just talking regardless of the strain sensing, all other sensing types, temperature, vibration, pressure, and so on, are basically depending on the strain sensing protocol. What I mean is that all entire sensors made of fiber break gratings basically relying on the strain sensing, but coming out with some model development, I must say, or with some numerical approach, we are converting the strain value obtained by the FPG sensor, and considering that we are measuring the temperature, vibration, acceleration, and so on. So here, in most of the case, we will be talking about the uniform gratings. The uniform gratings are those having the constant period in between, as I mentioned in the very early stage of the presentation. And when we look up the equation written in the bottom of the page, I see that the lambda b, which is break wavelength or reflected wavelength is equals to 2 times an effective times period. An effective is effective refractive index of the optical fiber, and it's constant, only changing with the type of optical fiber, and there is no any impact during FPG writing stage onto the effective refractive index. That's we cannot change. Let me go into more details. Although effective refractive index is a constant, any change in the grating period allow ones to have blue shift, which means lower reflected wavelength, or red shift, which means higher reflected wavelength. As you might see in the picture in the presentation, when there is no tension on the optical fiber and there is no change, there is no physical change on the optical fiber, the grating period stays steady, while if there is any tension applied on the optical fiber, that might be positive or negative force, or I can say that extension or compression. The break wavelength or reflected wavelength shifts accordingly. Okay, the amount of shift basically depends on few parameters. So in order to understand how fiber break grating sensors are properly working in terms of strain and temperature sensing, we have to divide them into two classifications, strain and temperature. So in this context, I must say, if I'm looking for the strain relation in the break wavelength, I should consider the equation written in the first one. Okay, in this equation, I basically see that the total change in the length of optical fiber is changing the break wavelength. Here in the first equation, I see the PE as a constant value, and that's equals to 0.78 for polyamide coated fiber. In this point, it's quite important to mention that in most of the FPG sensors, we are using the polyamide coated fiber. Just in some companies, the workers or the researchers are working on the acrylate optical fiber, which is quite harder than the polyamide, but polyamide is the first choice at most of the time. And besides that, we are operating the fiber break grating in the bandwidth of C to L. So here we are considering the grating, we are considering the break wavelength to be 1550 nanometers, which is right into the middle of 1550 to 1600 nanometers. So when I consider these two values and substitute them into the equation, I get that I have the sensitivity of 1.2 picometer for the each microstrain value. But here, just please note that this value is valid only for the bare fiber, which means there is no additional coating, there is no additional process, and so on. You get the fiber, write the fiber break grating into the core, and when you go to the measuring, you will see this 1.2 picometer per microstrain. But when we talk about the temperature, we see the same form of the equation only by substituting the strain parameters with the temperature parameters. Here, there are two important parameters I have to mention. The first one is alpha. Alpha is a thermal expansion coefficient, and that's equals to 0.55 times 10 to the power minus 6 per degree Celsius. And N is the thermal optical coefficient, which is equals to 8.6 to 10 to the power minus 6 per degree Celsius. These values are steadily constant, and we cannot change them physically unless we change the optical fiber itself. So when I substitute these two values into my equation, right into the middle of the paper, starting with the delta lambda b over lambda b equals to 1 minus PE times strain Z, I get the result of 10.2 picometer per microstrain, which means when I montage my optical fiber break grating into some sort of specimen, let's say it's an alloy, and I keep the temperature value constant, I will keep getting the same result. But if in case the total temperature in the environment changes, let's say 5 degrees Celsius, then without considering any strain, I will see some reflected wavelength shift in terms of 10.2 picometer times 5, and that's equals to basically 51 picometer. Okay, so as I have given an example, even if there is no any change in the strain value, if environmental condition change in terms of temperature, I will observe that there are some physical effect on the optical fiber. In this case, I might confuse is the cause of this shift coming from the strain or is it coming from temperature? So in order to understand and evaluate the difference between them and only observe the strain change and track the strain change, I have to compensate the temperature and temperature effect on the fiber grating structure. So for this purpose, the researchers have gone through like lots of approaches, but I have picked the mostly used 3 of them. The first one is using an additional reference temperature sensor. Okay, this is the most reliable approach as compared to others. But in this case, in this approach, the gratings are bared. They have no protection, no sealing, and so on. Why? Because I want my temperature sensor to indicate each and every single change within the environment. So, and besides that, with this approach, I will add some additional cost to my optical fiber sensing system. And moreover, I will be having a limited strain sensing. Why? Because the temperature is, how to say, temperature sensitive, 10.2 picometers per degree Celsius. And in some environments, there are like the temperature range within a day goes up to 30, 40, maybe 50 degrees Celsius. So it will limit my strain sensing as well. Besides that, as I told you, although I'm using the bare fiber in this approach, they are so fragile, and I cannot use this type of sensor in the harsh environment. So I'm just passing through the second approach, which is glass tubing temperature sensor. Okay, this is applicable to the some let's say basic applications, the conventional applications. I'm not talking about the harsh environment. Okay, in this approach, we have one Fpg sensor array made of 2 black gratings. The first one I have shown in the picture is epsilon, with the epsilon is sensing only the strain, while the other one sensing only the temperature. Okay, here the point is that the red tube shown in the second picture is a quartz tube. It's like fully quartz, fully glass, I must say. So it's quite fragile. And here I cannot increase the width of the tube because I want entire temperature effect to be indicated by the sensor. And I have to cut the optical fiber within the tube because I want to leave my temperature sensor to be strain relief, and so that it will not be getting affected by the strain changes. Okay, in this method, the obtained results are relatively unreliable. Why? Because the temperature within the tube is released freely. So if the flow changes, the flow in the air changes, the sensor will start to shrink and it will be sweeping. So I will see some additional noise within my system. And of course, it requires some additional cost because the tube I mentioned here is much more expensive than the Fpg sensor. And also I have to use some specific and special epoxies and glues for this sensing approach. Moreover, it has relatively lower accuracy.
So colleagues, try to be a little bit faster. We have very short time.
Yes, so... yes, sir. Yes, I'm already on the middle. Mm-hmm. And finally, we have sensor array packing approach. With this approach that's studied in this thesis, you will achieve most reliable compensation, just like using additional reference sensor. It's easy to apply, and it provides the maximum durability. Okay, so one of the most important points that I have to mention, FPG sensors are used like dramatically in the air vehicles, such like the one you see in the picture, the UAVs. Here we have some problem when we just load the optical fibers into the UAVs on the ground, and when they go to the air and just fly like around 30,000 feet, we see some temperature change up to minus 60 degrees Celsius. So our sensors, in most of the case, they cannot be reliable at that point because it's a freezing point. Therefore, we have come up with a package structure, and this package structure allows us to compensate the temperature effect and only allow us to use strain sensing. And here, but still, we have to be agree with that. The temperature, the value might change within a length specimen. So we have to put some measuring points, measuring spots into the wing or anywhere in the body, and just to understand the distribution of the temperature within the body itself, and only that way we can measure the strain results properly. Okay, this is the package structure actually we have created for the study. In this package structure, we have kept the width as low as possible. Although it's stainless steel 316, we have the thickness of 0.4 millimeters, and some parts of the package has been manufactured by 3D printing. In this package, we have two slots. At the first one, we are placing the FPG for strain sensing, and other one goes for temperature sensing. If you look at the package structure for the temperature sensing, it doesn't have any connection with the end side of the package. So thereby I can say that any impact on the temperature sensor in terms of strain change doesn't dramatically change my temperature sensing, while all of the indications can be observed by the strain sensor here. And here I can finally say that the tension applied to the optical fiber is greatly transferred to the package, and so distributed through strain and temperature sensors, so that as you may remember in the first slides, I mentioned that the strain sensing for the bare fiber should be 1.2 picometer per microstrain. We finally achieved that value, as you might see in the picture. We finally achieved that value, although we are using a package. So here we have. So let me just go a bit more faster and talk about the results. Mm. We have three types of tests that's a must to do for a properly working optical fiber. The first one is no load grip test. Grip test, we are considering the grip test in order to understand the effect of the epoxies and some other additional materials we are using for mounting the optical fiber to the package. So here we see that we have gone through for 3,000 minutes, which is 50 hours, and we just released the optical fiber package without any tension in the stable environmental condition, and we have seen that after 500 minutes it stays steady. So which means if you manufacture such sort of optical fiber, you have to keep the optical fiber at least for 500 minutes to get into this steady level. So in order to understand how it reacts under load, we have done a under load grip test. In this test, actually, according to the results we received from the ANSYS that we have seen, our package structure shown on the left picture is durable up to 115 newtons from the spot load. So we decided to use a load that's equals to 140 newton, and in 14.65 kilograms in terms of the weight. And we have seen that when I just hang the the load and tie it with the grating package, I see that after like 70 or 80 hours, it stays steady and it doesn't change. It means if you want to measure some like very sensitive, I mean, you have a very sensitive measuring case, you have to first montage your optical fiber to the specimen and wait for 8 hours for the most precise result. And finally, we have gone through a tension test, and this tension test was handled in Bursa Technical University with using Shimazu AGX 250 kN tensioning system, and we have loaded the optical fiber package like respectively starting from 0 to 15,000 Newton, and we have seen that the three specimens we have achieved have the highest had highest durability as compared to the conventional ones that we are using and we are buying from the sensor industries. Even in the air vehicles, I must talk about the UAVs. The maximum strain we see in the UAVs in the extreme conditions does not exist 40,000 microstrain. But in our experiment, the sensor which has the lowest durability even goes more than 5,600 microstrain, which means the manufactured sensors are surely suitable for the UAVs and other air vehicles going through 30,000 feet. And here is the last result I will be talking. As you might see from the picture right bottom corner of the page, the strain sensing is shown with the green and temperature sensor shown in the red. Until the 15,000 microstrain, there is not even a single change in temperature sensor, which means we have been successfully kept the temperature sensor as strain relief. And this product is just capable of indicating each and every single change in sensing and compensating the temperature effect on the package. So finally, I would like to thank to TÜBİTAK, Ermaksan Machinery, and Bursa Technical University, and of course Turkish aerospace companies, just for supporting me during these studies. Thank you for leaving your time, and I might now accept any questions if you have.
Thank you for the presentation. So we have time for very short question only, if some from colleagues wants to ask.
Okay. Okay, I guess no
so
questions, sir.
I think there is some questions, so please.
Okay. Yes, okay. That's a quite nice question, actually. I was planning to mention about that as well. Of course, if in case you are doping your optical core with the fluoride or some special materials just like ytterbium and so on, you will have much more photosensitivity than using the conventional optical fiber. But in this case, you have to consider that when you dope the optical fiber, you have to keep the fiber in like under condition of -45 to -50 degrees Celsius to keep the doping inside the optical fiber's core, and only take it out when you go for the manufacturing process. Unless, other than that, you have to keep it very precisely under -45 to -50 degrees Celsius. But for sure, you will have much more better, how to say, growing in terms of fringes. I hope that answers your question.
So thank you for reading a question from the chat.
Sure, sir.
If there is not any other question and the colleague is satisfied, so I thank you again for your presentation, and we can move to the second paper, second contribution, entitled BOTDR-based distributed acoustic sensing, proposed by Mert Bilgen and Abdurrahman Gandey from the National Defense University, Turkey. So I can, yeah, okay, thank you. You are here. So please start and be very accurate and in your presentation, because we have only limited time.
Okay. First of all, thank you for your participation in the organization. I am Mert. I work at National Defense University, Department of Electronic Communications Technology. I will make our presentation to ELECO 2021. The title of our presentation, Fast BOTDR-based distributed acoustic sensing. As you can see from this slide, the contents of my presentation include introduction, temperature dependence of the Brillouin power change, temperature dependence of the phase change, simulation results, conclusion. Now, I will first talk about scattering mechanisms such as Rayleigh, Raman, and Brillouin scattering. In recent years, optical fiber distributed sensing systems have been used extensively. In other words, OFDS systems have become crucial for detecting and measuring the physical quantities such as temperature, strain, vibration, and pressure formations simultaneously in real-time applications. These systems generally make use of Rayleigh, Raman, and Brillouin scattering mechanisms formed in the waveguide, i.e. optical fiber, which is used as the sensing element. As a matter of the nature of light, characteristics of light wave-like frequency, power, and phase are changed by the formations of temperature, strain, vibration, and pressure as the light photons travel through the sensing fibers. The backscattered optical signal consists of Rayleigh, Raman, and Brillouin components. Spectrum related to these components are shown in figure 1. The temperature and strain sensitivities of the Rayleigh components are quite low in comparison to the Brillouin component. Therefore, it can be considered to be insensitive to the factors such as temperature and strain. On the other hand, Brillouin-based methods are more applicable for distributed sensing of temperature formations because of their high sensitivities of these measurements. Distributed acoustic sensing, also known as distributed vibration sensing, is an optical fiber sensing method depending on the phenomena using Rayleigh scattering. In this kind of distributed sensing method, optical time domain reflectometry, OTDR, is utilized for getting time and location information where scattering of light wave has occurred along the sensing fiber. In OTDR-based method, acoustic changes and vibration formations occurring along the fiber cause a shift in the phase of the backscattered optical signal. The phase shift and phase change information reached along the sensing fiber are obtained by subtracting a phase OTDR trace from an early stored trace. In optical fiber distributed sensing systems, mainly utilizes reflectometry interrogations method for detecting measurements. The most common methods employing reflectometry interrogation can be evaluated as OTDR, BOTDR, BOTDA, POTDR, and OFDR in applications in the field. As the light passes travel into the sensing fiber, scattering losses occur in the medium, mostly caused by Rayleigh scattering. BOTDR method, which in principle is substantially similar to the optical time domain reflectometry, is based on the Brillouin scattering mechanism resulting from the interaction between an incoming incident light wave and thermally produced acoustic waves in the sensing fiber. This method exploits spontaneous Brillouin scattering and needs access to only one end of the fiber. The locations of the sources of measurements along the entire length of the sensing fiber are specified by utilizing the time interval between pumping the incident light wave and detecting the backscattered light wave. In the study, a method based on the phase BOTDR is proposed for attaining the phase shift and change formation occurring along the fiber depending on the temperature effects existing in the medium. This method is differently from phase OTDR. It employs the Brno scheme for distributed measurement of phase information in the system. In the system-based open BOTDR method, Brno power change and frequency shift of the backscattered signal are exploited to obtain temperature information occurring along the sensing fiber. The Brno power change along the entire length of the sensing fiber is expressed as given in equation 1. S is the capturing coefficient defining the amount of scattered light captured from the numerical aperture of the sensing fiber and is expressed by equation 2. The Rayleigh and Brno scattering coefficients used in the Brno power change are stated as given in equation 3a, 3b respectively. The parameters and values utilizing in the equations are given on the slides. In BOTDR-based temperature sensing, temperature profile along the fiber can be obtained from the temperature dependence of the Brno power change. Temperature dependence of Brno power change for zero strain is given with equation 4. In distributed acoustic sensing systems, when an external vibration effect is generated on the section of sensing fiber or a quantity change occurs, fiber length and the core refractive index of the fiber will vary linearly. Any change made in refractive index causes both the phase shift and the phase change on the optical signal pumped into the fiber. At the moment when the change happens, distance information is obtained using the correlation between time delay and the speed of light. The optical phase shift can be written as a function of core refractive index and quantity length of the sensing fiber as given by equation 5. The phase change existing along the entire length of sensing fiber is stated as mentioned in equation 6. The core refractive index and fiber length are affected by changes in thermodynamic quantities such as local density, entropy, pressure, temperature, and stress. In this context, delta NL change can be described depending on the temperature variation with equation 7. Spatial resolution delta Z instead of the unit change in fiber length and reorganizing equation 7 takes the form in equation 8. The phase change can be given as in equation 9. Temperature dependence of the core refractive index of the sensing fiber can be described by equation 10. When heating the fused silica fiber, longitudinal change delta L takes place along the sensing fiber depending on the parameters of thermal expansion coefficient, initial length of the fiber, and temperature variation. Taking the initial or original length of the sensing fiber is equal to the spatial resolution. Longitudinal change can be stated as equation 11. The sensing model of phase BOTDR based distributed acoustic sensing employed in the study is illustrated in figure 2. In the sensing model used in this research, a pulsed laser source produces optical signal with the output power of 1 milliwatt operating at 1550 nanometers. Optical pulses passing through the sensing fiber are amplified using erbium doped fiber amplifiers EDFA1 and EDFA2. Thermal effects for getting phase information along the sensing fiber are modeled making use of O1 and O2 positioned at different fiber regions. Acoustic modulator AOM is added next to the EDFA1 to suppress ASE, amplified spontaneous emission, noise generated at the end of the amplifier. The circulator is utilized. Circulator is utilized for both routing the optical signal towards the ovens and Brno components of the backscattered signal to EDFA2. The band pass filter allows all the frequencies to be filtered whilst it passes frequencies within a certain range. The data analyzer unit. The data analyzer unit is exploited for processing electrical signals and getting information related to the temperature dependence of phase change in the system accordingly. Locations of the ovens positioned along the sensing fiber are mentioned in table 1. We use the ovens in distributed acoustic sensing configuration in order to model the temperature formations along the sensing to fiber. Simulations have been accomplished using MATLAB 2020B on the model based on the phase BOTDR for analyzing the temperature dependence of phase change in this research. In the model, thermal effects on the sensing fiber have been modeled by placing two ovens having different heating capacities along the fiber cable. Temperature profile for the sensing fiber with the length of 2,500 meters is shown in figure 3. As seen in the figure, there are two hotspots where the ovens are positioned along the sensing fiber. In these fiber regions, the height temperature values have been observed as 298 Kelvin and 197.5 Kelvin at the 619th meter and 1993 meters respectively. Phase change due to the temperature variation along the sensing fiber is illustrated in figure 4. In regions where sensing fiber passes through the ovens, i.e. in ranges of 600 meter, 625 meter and 1980 meter, 2000 meter, phase change reaches the maximum values with 227.7 radian and 214.2 radian respectively. It is clearly seen from figure 4, as the temperature increases, delta NZ shows a tendency to rise linearly. In other words, the higher the temperature is, the greater the delta NZ is. For room temperature of 293 Kelvin, delta NZ gets the value of 0. Simulation related to the relation between temperature variation and delta NZ change in the temperature range of 290 Kelvin, 350 Kelvin is shown in figure 5. For getting the simulation indicated in figure 5, interpolation method is employed to have temperature information along the sensing fiber, and thus linear formula representing the temperature dependence of delta NZ change is obtained as in 12 for given temperature range. Simulation concerning the temperature dependence of phase change is shown in figure 6. As obviously seen from the figure, temperature formations occurring along the sensing fiber cause to increase the phase change linearly. Using 9, 10, 11, and the methods of curve fitting and interpolation linear equation related to the temperature dependence of phase change is derived as in equation 13 for temperature values changing in the range of 293 to 198 Kelvin. Phase change occurring along the sensing fiber vary between 0 radian and 227.7 radian. When taking the first derivative of 13 to temperature, variation ratio between phase change and temperature can be attained. In other words, a 1 Kelvin variation in the temperature of the fiber core causes 45.667 radian variation on the phase change. Relation between phase change and delta NZ is plotted as indicated in figure 7. As it is obvious in this figure, phase change occurring along the sensing fiber is linearly affected by variation of the parameter of delta NZ. Benefiting from 12 and 13, the first order equation with respect to the relation between phase change and the parameter of delta NZ is obtained by equation 14. Fiber core refractive index dependence of phase change is shown in figure 8. For refractive index values between 1.44183 and 1.44188, phase change gets the values in the range of 0 radian and 227.7 radian. As you can see clearly from figure 8, there is linear relationship between phase change and core refractive index of the sensing fiber. In case of making change of refractive index of fiber core, doping process is performed by adding little amount of other chemicals during the production. Therefore, any fluctuation existing in value of core refractive index of the sensing fiber will affect phase change of the backscattered Brillouin signal guided within the sensing fiber. In the study, a new phase BOTDR based method for distributed acoustic sensing of the phase change occurring along the sensing fiber has been proposed. In this context, a sensing model has been constructed for making analysis related to the temperature and core refractive index dependencies of phase change, and the relevant simulations have also been performed using MATLAB. The detection model was created and the related simulations were made using MATLAB 2020B. Moreover, the linear equations related to the dependencies of temperature and core refractive index on phase change have been acquired for temperature variation in the range of 293 Kelvin and 298 Kelvin. Phase change shows an alteration between 0 radian and 227.7 radian, and core refractive index varies in the range of 1.44183 and 1.44188. Therefore, a 1 Kelvin variation in the temperature of fiber core causes about 46 radian changing on phase change, and variation in value of 1.03 multiple 10 to the minus 5 core refractive index of the sensing fiber. Considering the effects of temperature change in distributed detection systems, more effective and suitable designs can be made for field integration detection systems for future studies. Herewith, this study forms a background for future investigations and projects related to optical fiber distributed acoustic sensing systems. Furthermore, it gives valuable insight for future works on the relation between temperature, core refractive index, and phase change formations in the sensing medium. Thank you for listening to me.
Okay, thank you, colleague, for your interesting presentation. So we can open a discussion. I have one question from site Esther Karlik. I can read it. I don't know if you see that message or not. So he is asking this question: what are spatial and temperature resolution in your simulations? How did you determine item?
Yeah. We used the equation of spatial resolution, delta Z, since it is depending on C multiple tau divided to N. Spatial resolution has been computed as 1.041 meter approximately. Yeah.
Okay, you answered this question. So if someone, the same colleague is asking temperature resolution, so you can react on this question.
The number of measurements points for our DAS distributed acoustic sensing model we used in this study is about 2,400. We have computed this value by dividing sensing fiber length with spatial resolution.
Okay. So there is also a question, what is the number of measurement points for DAS system used in your model? So Abdurrahman Gainday is asking some detail, so you may react.
Yeah, I answered. The number of measurements points of of our distributed acoustic sensing model we used in this study is about 2,400. We have computed this value by dividing sensing fiber length with spatial resolution.
So, okay. If no other questions, so I can again thank you for your presentation, for your interesting topic, and we can move to another colleague with his contribution entitled earthquake detection using fiber optic distributed acoustic sensing, provided by Hasan and colleagues from Istanbul Technical University. So, like, you can. Thank you. And Hasan, yes, you are here. So I introduce your paper now, so you can start with your presentation. So please keep 15 minutes and 5 minutes for discussions, because we are very tightened time schedule now.
Okay, I will keep it short. The screen is okay. Everybody can see. Yeah. My name is Hasan Yetik. I'm working on TÜBİTAK Research Center in Turkey. I'm pursuing my PhD degree in Istanbul Technical University. My advisor is Selcuk. And my overview of the presentation starts with abstract. I'm going to read out loud to give brief information about our research and our paper. And I'm going to start with introduction and explain our experimental DAS system, and talk about the seismic data collection and give the results at the end. And in the last 2 decades, fiber optic distributed acoustic sensing has gained popularity within many fields, including seismic analysis and intrusion detection application. In this paper, we propose a I'm sorry. Let me take this. Okay. In the last 2 decades, fiber optic distributed acoustic sensing has gained popularity within many fields, including seismic analysis and intrusion detection application. In this paper, we propose a fiber optic dust scheme for earthquake sensing and data analysis purposes. Using our modified dust setup, which is previously used for intrusion detection, we successfully recorded many earthquakes with epicentral distances ranging from 12 to 1,319 kilometers and magnitudes from 1.1 to 6.9 within the time period of August 2019 to August 2021. The utilized communication fiber optic cables lie approximately 50 kilometers southeast of Istanbul and has length of 4 and 25 kilometers. In this paper, we are presenting our experimental dust system in detail and our contribution to the seismic sensing using fiber dust. To observe and analyze seismic events, there are 3-axis seismometers, and they are frequently used. Seismic sensing accuracy can be readily increased by increasing the number of these seismometers, but due to the high deployment cost and adding a new seismometer to a sensing network can be time-consuming and expensive, unfortunately. Additionally, deployment of seismometers in dense urban areas, seas and oceans require more labor, time, and liability costs. Under such conditions, in order to mitigate these problems, fiber optic distributed acoustic sensing technology can be used in place or in addition to seismometers to some degree. To detect physical impacts on fiber optic cable, optical time domain reflectometry based on Rayleigh backscattering is commonly used technique. Rayleigh scattering in the fiber cable is caused by small density changes which are frozen in the fiber core during manufacturing process. This is unavoidable due to the nature of the manufacturing process that includes melting and hardening of fiber core. Although this phenomenon seems to be a downside, it's actually favorable for dust purposes. In this technique, modulated narrow laser light pulses are used to excite fiber optic cable, while excitation pulse advances in fiber core. Rayleigh type backscattering occurs due to the impurities mentioned earlier, and there is no physical impact on the cable. Backscatter light intensity and the phase is low and zero, but when the cable is exposed to physical impact, such as squeezing and acoustic signals, intensity of the Rayleigh backscattering increases proportional to the impact strength or vibration or acoustic signal power. The dust technique is commonly used in following fields: intrusion detection, pipeline security, mining, railway monitoring, and so on. The first utilization of the dust was targeting geophysical research applications conducted by the petroleum companies. Application areas of dust expanded to cover regional and global seismology research interests recently, and readily available fibers are utilized as seismic sensing arrays by many scholars from Spain, Japan, and United States of America recently. Since there are abundant amount of unilluminated and unused, in other words, dark telecommunication fiber cables around the world, researchers are attracted to experiment with dust technique in dark fibers to study seismology based on fiber optic distributed acoustic sensing. In fiber dust sensing, fiber cable is considered to have equal space virtual sensors which sense acoustic signals or vibrations. Sensor spacing is determined by the spatial resolution of the system, which is, I'm going to explain how is set in our system. And the fiber dust technology offers high spatial resolution depending on the laser pulse duration. Fiber optic dust technology provides synchronous sensing and data collection from huge number of sensing points in the fiber cable, which is neither easy nor economical for other types of sensing networks, such as ones based on seismometers. It also doesn't require any special type of fiber cable. It can work in readily available telecommunication fiber cables, standard fiber cables, communication cables, actually. So our experimental dust system, it is based on phase-sensitive optical time domain reflectometry, which is the most popular and widely used technique in fiber optic dust systems. This technique relies on Rayleigh backscattering in fiber medium. To observe seismic events, we propose the fiber dust scheme that is based on phase OTDR with coherent detection. The proposed dust scheme we can see on the figure or on the slide. The proposed dust scheme is based on our fiber optic based acoustic sensing system, which in short FOTAS, and is published 2 years ago. And our dust scheme can be divided into 3 major components. So to say, optical interrogator, electrical signal analysis and storage system, and the fiber optic cable. Optical interrogator. A basic configuration of an optical interrogator consists of an continuous wave laser source with very high frequency stability, and an acoustic optic modulator, and a 1x2 power divider, and a 2x2 coupler, a circulator, and a balanced photodetector. Main task of this unit is to modulate continuous wave laser light with a given pulse shape and duration from the electrical signal analysis and storage system. The modulated laser pulses are fed to the fiber cable through circulator, and the backscattered light signals are fed to the balanced photodetector through circulator and by 2x2 coupler. The balanced photodetector translates the received laser light into the electrical signal and conveys its output to the electrical signal analysis and storage subsystem. The noise induced by electrical and optical components regulates the overall performance of the system dramatically. To mitigate, to reduce the electrical noise, we have adapted radio frequency filters and digital signal processing algorithms. And an acoustic modulator is chosen to modulate the laser in order to have a high optical extinction ratio instead of the electro-optical modulator, which has fairly less extinction ratio than the acoustic modulator. We also preferred coherent detection over direct detection to improve the receiver sensitivity and balance photodetector with a high common mode rejection ratio, which is greater than 50 decibels, with the intention of improving SNR of the received signal. And the electrical signal analysis and storage system. This is a fairly simple subsystem. This subsystem incorporates an RF transmit and receive electronics and a computer with data storage devices. This unit is responsible for generating excitation pulses with carrier frequency at which the acoustic modulator resonates. Also, this unit receives electrical signals from balanced photodetector for further processing, and the balanced photodetector output contains a backscattered signal centered on the 100 megahertz, which is the resonance frequency of the acoustic modulator. So the received signal first demodulated with an optical local oscillator, and then with an RF local oscillator, which is 100 megahertz. Then these signals are first filtered with an RF bandpass filter, down converted to baseband, and filtered using appropriate RF mixers and filters. A resulting signal is digitized and transmitted to the computer for further digital signal processing and noise reduction. Actually, RF signal conditioning, down conversion, digitization, and some of the RF filtering jobs are held in AD9364 RF agile transceiver from analog devices that is repurposed and programmed specifically for DAS use by us. And this is the most important part of the project. The fiber optic cable plays the crucial role on the DAS system. It actually half of the system, and just a single cable can make you better at sensing DAS or worse. Its location and its coupling characteristics very important in this field. For fiber optic DAS sensing, we have used 2 different fiber cables, which are, the first one is a 4 kilometer long buried telecommunication cable in the Gebze premises of TÜBİTAK, which we named as short fiber optic cable, which is approximately 50 kilometers southeast of Istanbul and nearly 10 kilometers north of the Marmara fault line. And the second one is 25 kilometers long buried telecommunication fiber, again which we named as a long fiber optic cable, lies between the Gebze and Yalova. It crosses the Gulf of Izmit. And the second cable has submarine portion that is around 5 kilometers long, lies under Gulf of Izmit, approximately 40 kilometers southeast of Istanbul, and crosses over Marmara Fault Line. The Marmara Fault Line, which is expected to produce an earthquake with a magnitude of 7 or more in the near future. What the fiber cables used in this work go through many fiber junction boxes, which consist of splices and connectors. Each connection introduces attenuation to the light in the fiber medium, hence reduces the signal quality and maximum range. Also, they were laid underground many years ago, and the sole purpose of the fiber cables is actually communication. So the coupling between fiber cable and the earth is unknown. And the field tests can be conducted to identify the areas or points that have coupling problems in order to better use of the fiber cable. So seismic data collection, we have been recording dust data since August 2019. Earthquake events are monitored and filtered using data that is provided publicly by Kandilli Observatory and Earthquake Research Institute, Regional Earthquake and Tsunami Monitoring Center, thanks to the Bosphorus University. Selected earthquake events are extracted from dust recordings and logged to be processed. Set of earthquakes detected between these two dates are presented in the results section. We are able to detect most of the earthquakes which are occurred inside the border of the Turkey and the time interval between the given dates, which have magnitude ranges from 1.1 to 6.9, and the distance ranges from 12 kilometers to 1,319 kilometers. The nearest detected earthquake occurred in Istanbul, Turkey, which has magnitude of 1.1 and has a distance to fiber optic cable of 12 kilometers. Farthest detected earthquake occurred in Turkey-Iran border region, which has magnitude of 6.2 and has a distance to fiber optic cable of 1,319 kilometers. The dust system we've been using configured to have 17.5 or 25 meters of spatial resolution and pulse repetition frequency of 500 or 1,000 hertz, depends on the recording section we have. So I'm going to continue with the results, and here we can see in the figure we have a histogram of earthquakes. The x-axis represents the magnitude and the y-axis the distance to fiber optic cable. This is not the distance to the electric signal and analysis system. It is actually distance to the fiber optic cable, the virtual sensor, from virtual sensor to the epicenter of the earthquake. A histogram on the right depicts the detected earthquake by our experimental dust system while providing their distance to the fiber optic cable and magnitude. The detection accuracy varies with the both magnitude and distance to the fiber optic cable as seen on the figure. In other words, accuracy detection distance to fiber optic cable is exponentially proportional to the earthquake magnitude actually. The histogram includes data of 266 earthquakes, which has minimum and maximum magnitudes, as I said before, 1.1 to 6.9. And the z-axis represents the detected earthquake count for a given point. This is the dust recording of Istanbul, Turkey. Magnitude of 5.7 earthquake is given in the right. P and S waves given the earthquake can be clearly seen. From early to late, we can see the P waves, the primary waves comes first, and the secondary waves, the S waves comes later, and we can clearly differentiate these two in so to say many points. not in all virtual sensing points, but most of the points we can differentiate these two. So this recording captured with a spatial resolution of 17.5 meters, a PRA and pulse repetition of 1000 Hertz. Data is decimated with a factor of 10. And this is the time series of a given earthquake, which occurred in Istanbul in a magnitude of 5.7. As we can see the graphs, seismometer and our experimental data system can sense earthquake with a similar sensitivity and quality as shown in this figure. And in both time series given in the figure, this figure, the P and S waves of given earthquake can be clearly seen. Also, dust channels. We didn't do that in this graph, but dust channels can be stacked to enhance dust signal quality when single point measurement is sufficient, because there are many sensing points laid on the fiber optic sensing, so to say. And this is an interesting result of our experiments. We can see the wavefront of the earthquake occurred in Yalova, which has magnitude of 2.8, which is fairly close to our sensing fiber. Due to the time of, I'm sorry, let me quick check this. Yes. This dust recording captured with spatial resolution of 25 meters and pulse repetition frequency of 500 Hertz, and data is again decimated with a factor of 10. And P and S wave of given earthquake and its wavefront can be clearly seen. Using dust recording with a clear wavefront like this, like in this figure, one can locate the epicenter of the earthquake easily using time of arrival methods. We would like to show the wavefront for this purpose. We are planning to locating epicentral distances of the epicenters of the earthquakes using such dust recordings in the near future. And this work shows that the fiber optic dust is promising technology in seismology, as in the other fields like intrusion detection, perimeter security, structural health, and so on. And our experimental dust system is fairly simple compared to the state of the art that may include optical filters, different interrogation methods like Brilliant and fiber graded fibers, and so on. But the performance of the proposed system can be improved by developing advanced DSP techniques utilizing optical amplifiers, filters, dedicated fiber optic cables, which are solely laid for dust use. But dust purposed fiber optic cables are expected to have maximal earth-to-cable coupling, no or minimal number of splices and connectors along its path, laid in order to avoid man-made noises. Although such fiber optic cables are desirable for the dust application, but in reality, it is nowhere near realistic due to the very high installation cost of the fiber optic cables. We generally using the dark fiber cables in order to minimize the installation cost, which makes the dust fiber optic based dust seismic researches very popular. Even with a simple dust system like ours and regular communication fiber optic cables, we are able to detect earthquakes with distances reaching 1,319 kilometers successfully using 4 and 25 kilometers long standard fiber optic cables, which are previously dark cables, with the help of simple DSP techniques. Although fiber dust is not ready to replace conventional seismometers yet, but we think that fiber dust will augment them when more efficient and cost-effective data collection is required due to the financial or geographic constraints. And these are my references for this presentation. And thank you all for listening to me.
Thank you, Hasan, for your presentation. So there is one question. Two questions are here. Can read it for you, or you can find it in question and answers on the bottom of your screen. So the first question is how to determine the magnitude and location of the earthquake with this type of sensor. And can you give us some additional information about conversion mechanism used in this sensing?
How to determine the magnitude and location of the earthquake with this sensor? The magnitude, determining the magnitude of the earthquake is not possible with this type of sensing scheme, because this type of distributed acoustic sensing schemes cannot measure the known unit of impact on the fiber cable. They only change its intensity and the phase under some physical impact. But the location, to determine the location, we can use the time of arrivals, because we can clearly record the P and S waves. I've given the time series of the recordings, which are from seismometer and the dust recordings, which are pretty similar in terms of phase and amplitude variations. So determining the location of the earthquake is possible with this type of system, but determining the magnitude, we need to obtain either velocity, acceleration, which are derivative of vice versa, and or the strain or velocity. We need to measure these two and calibrated measurements. They have units and they are calibrated. Our system produces an arbitrary unit outputs signals, and which cannot be used to determine the magnitude actually.
So the next question from anonymous colleague is how can you increase the resolution of sensing?
How can you increase resolution?
The resolution.
The resolution. I think he's asking, or he or she asking about the spatial resolution. The spatial resolution is controlled by the pulse width of the excitation pulse. It is generated from, as I said before, electrical signal and analysis subsystem from in our system. If we set it to 1 microsecond, it represents to 1,000 meters of spatial resolution. If we use the 100 nanometers of pulse width, it generates a spatial resolution of 100 meters, which can be controlled, but it can it actually determined by the fiber length and depends on the pulse repetition frequency, but to some degree it can be adjustable.
And the last question, or two last questions, are from the Abdurrahman Gendi again. So in your detection system is some pulse duration. So he asking on the pulse duration time of the optical source, which is used for resolution, spatial resolution, about 17.5 units.
Let me calculate it. As far as I remember, it should be around 175 nanoseconds, as far as I remember.
And his last question is, which kind of scattering mechanism did you exploit to get vibration information about vibration with respect to earthquake event?
We exploited the Rayleigh backscattering mechanism in this work. As I said before, the phase sensitive OTDR and coherent detection we utilized for our experimental dust system, and the Brilliant scattering is usable for this purpose. We have planned to use Brilliant scattering for this purpose to detect vibrations and temperatures, as some of the colleagues presented just before me. But due to the economical and the project constraints, we cannot move to the Brilliant scattering side of the distributed acoustic sensing, but it is possible to use the Brilliant scattering for this purpose. The Brilliant scattering may provide a measurement with a unit, actually, as far as I remember. That's a good question, actually.
Okay, I think all questions were answered. If colleagues have some additional questions, please feel free to write to chat while we are discussing or presenting next paper. So thank you again for your presentation. So we have to move to another and last presentation in our session. So thank you again, Hasan, and I would like to invite Mahsa Ghavami from Sharif University of Technology, Iran, with the paper having title Considering Uncertainties in Charging Control Plug-in Electrical Vehicles.
Hello and welcome to my presentation. My name is Mahsa Ghavami. I'm from Sharif University of Technology. I'm a PhD student. Yes. Can you see my shared video?
Not yet. Not yet, but try to be fast because we have a very limited time. So.
Yes. Is everything okay?
No, we are not seeing your screen.
Yes.
Now.
Can you?
Yes. Yes, it works.
Considering uncertainties in charging control of plug-in electric vehicle. Yes, nowadays big cities encourage people to use plug-in electric vehicle due to reduction of fossil fuel resources and air pollution. Existing policies around the world suggest healthy growth of plug-in electric vehicle over this decade. For example, in the sustainable development scenario, the global EV fleet reaches 230 million vehicles in 2030. Owing to detrimental effects of charging large population of plug-in electric vehicle on power grid, coordinated charging, discharging strategies have attracted much attention. Coordinated charging, discharging method can be categorized into decentralized and centralized method. In centralized method, a central controller determines charging rate by collecting information from all PVs. Which could cause large online computation time, and in addition, this approach do not permit all PV owner to determine their charge preference. In decentralization, in order to decrease online computation for large population of PVs, each PV directly ascertain its charging preference based on their own authority and something like this. One of decentralized optimization method is to avoid charging during on-peak time and fill valet during off-peak time is valet filling approaches, which is defined in these two papers. In our paper, we use valet filling property. Okay. In practice, PVs may have different initial state of charge, may have different arrival time, may have a different departure time, and the numbers of PVs which enter charging station at each time slot may differ and may change. In this paper, we want to model charging control of each PV by using different values for these uncertainties. In other words, we approximate the centralized solution of the centralized solution around nominal values of these uncertainties. In our method, there is no need to solve any centralized or decentralized method or in addition, this ensures privacy of each PV and require less online computation time than centralized method. And at end, in other words, the system is dynamic with EVs with different battery type that coming and departing all the time. For this reason, it is not possible to have a stationary and long-term charging control. To tackle with the system condition dynamic, we have proposed an algorithm which is based on MPC approach, and we implement it online. At first, we want to define our charging model. Charging model for each PEV defined in this way. The state of charge of each PEV, for example, the nth PEV, is defined by XNT. And there is some constraints for determining admissible charging control and state of charge. Our proposed model is based on a solution of the centralized optimization problem, this problem. There is one decentralized approach which is based on mean field game method in this paper. And in this method, each electric vehicle solves its own optimization problem and send its solution to one aggregator. The aggregator broadcasts mean field term to all PVs, and we want to compare this online, the online version of this algorithm with our method. For our method, at first, we want to model these two uncertainties, initial SOC and departure time of each EV. Design parameters of the model are K1X, K2X, K1T, and K2T. At first, we assume all PVs have nominal initial state of charge and nominal departure time in this way. For this case, UNNUM is defined here, can be determined by solving one centralized optimization problem that introduced later. Okay. Now, for determining all these coefficients, we want for example, we assumed, for example, for n equal 1, by changing its own initial SOC around a nominal initial SOC, changes of solution of a decentralized manner around nominal value is obtained. K1X, for this reason, is a linear approximator of these changes. Now we change initial SOC of another PV, for example, the second one, and measure its effects on charging control of the first PV. In this way, K2X in this equation can be determined. There is similar procedure for determination of K1T and K2T. In this way, the parameters of the model is determined. Okay. From these figures, it is obvious that K1x and K2x solution of centralized method, changes of solution of the centralized method that are different from each other. In addition, by comparing the slope of these two figures, it could be concluded that effects of initial SOC of each PEV onto its own differ from how it is affected by other. Similar results exist for departure time in this way that the slope of these two clusters are different. Okay, in this part, I want to describe another type of uncertainties, source of uncertainties. At first, I want to describe arrival time, and the second, number of PEVs. And we want to model different arrival time, as I said, and the number of PEVs at each time slot. At first, I want to only model arrival time. For this reason, we classified plug-in electric vehicle based on their arrival time, and we consider one design parameter for all PEVs in the same class, in the class that they arrive at the same time. We consider one design parameters, as I said. Of course, similar to what has mentioned before, the impact of initial SOC and departure time changes of each PEV on its own differ from how others affected. Thus, we have considered distinct coefficients for K1xp and K1tp in this way. Method for calculation of K1x is that we change initial SOC of, for example, the first PEV which enter at the pth time slot, and changes of centralized dimension centralized optimization solution for this first PEV results in K1x. For calculation of K2 X initial SOC of one PEV, such as the first PEV that enter at the first time slot is changed. By calculation of changes of the first PEV, which enter at the pth time slot, K2X1P is determined. Other parameters in this equation are specified similarly. Okay. It is noticeable in this figure that for designing this model, we consider nominal number of PEV which enter charging station at each time. So the question here is that how changes of PEV numbers affect the model. For this reason, and for answering to this question, I should say that, for example, if changes of the numbers of PEVs that enter at different time slots equal to, we would design 2 power 12 models for each cluster. This could cause complexity in designing model. For reduction of this complexity, for example, we change the number of PEVs which enter at the first time slot, and we observe that in this figure it is shown that we observe that charging model of all PEVs which enter at time slots 1, 2, 3 have been changed more. As another example, we change the number of PEVs which enter at the second time slot, and we observe that charging model of all PEVs which enter at time slot 1, time slot 2, time slot 3, and time slot 4 have been changed more. Therefore, we can conclude that if changes of the numbers of entering PEV at each time slot equal to the numbers of charging model for all PEVs entering at time slot P is function of numbers of entering PV at time slot P minus 1, P plus 1, and P minus 2, P minus 1, P and P plus 1. Thus, the numbers of all designing model for entering PV at P is equal to power 4, which is fewer than 2 power 12. For online version of our algorithm, we used MPC approach. That the proposed online method for computing charging is summarized in this algorithm, which is based on MPC approach, which is known as receding horizon approach. In other words, after calculating charging control of each PV based on the model that I have mentioned, only the first element of calculated charging control is implemented. In the next time slot, charging station charging solution update the system information, and we redo the calculation as mentioned here. To show how effective the proposed model is, the normalized power of our method has been compared to the decentralized method that is illustrated here. In this figure, it could be seen that the normalized power in the proposed model is closer to centralized method than decentralized one. For this reason, it worked better. And for conclusion, I should say that we model effects of uncertainties on centralized optimization. We have investigated how design parameters of a model changes by changes of PV numbers, and we proposed MPC-based approach to tackle with the system condition dynamics. And we provide closer normalized power to centralized solution than decentralized one. Thanks for your attention.
Thank you for your presentation. So, may I ask auditory for some question, if there are? I don't think so. I have one question for you. What is the density of charging station in your country? You are proposing such algorithm for most effective charging process of the cars. So how frequently are present charging station in your country, for example, in cities or in a village?
Can you repeat? I don't have your...
Okay, I asking only very simple opinion or question regarding number of charging station in your country. How many charging stations are in your cities or in the village?
Okay. These days, charging station in my country have been increasing, and one of the most important one in Tehran, which is under supervision of Magna company, and I think it's anything and a cutting-edge technology that is progressing in my country.
So thank you very much for the question. If there are not, if you are on your answers, and if there are not any questions, so I can conclude. Again, I thank you for your interesting presentations, and I can conclude that very interesting session with very interesting papers has been prepared. Thank you for all presenters. I also thank for
And thank you so much.
All technical supports.
Excuse me, is there any question?
No. We are ending.
Thank you.
Welcome.
Goodbye.